Now here we just looked at a one-dimensional problem where the velocities were in one dimension. And I indicated that you should be able to, I've solved this first equation, the conservation of momentum, for V1, and I didn't put the bar there, V1 bar. And if we take that V1 bar and substituting in here, we'll end up with a quadratic equation for V2 bar. And if you solve that equation, which can be put in this form with constants A, B, and C, you recall that you're going to have this formula right here that you use. Now, in a more complex situation, we could have these two particles that hit each other, one coming here and one going this way. If it was going the opposite direction, you just make it with a negative sign. And when this hits that, they could bounce off at two different angles, an angle theta and an angle phi. And if that happens, then of course, the momentum in this transverse direction must add up to 0. And it's the momentum in this direction, using the cosines of both of these angles, that would give us the result in that particular case. So here you have both a V1 bar, a V2 bar, see V1 bar, a V2 bar, an angle phi and an angle theta, and you end up with one more equation. So you end up with three equations. What is that extra equation? We still have these two, but you have one in the perpendicular direction that comes from the sines of the angles. And that other equation is that M1 V1 bar times the sine of phi, that's the momentum in this direction, must equal to M2 V2 bar times the sine of theta. And that balances the momentum going this way and the momentum going this way as these two particles careen off of one another. So we know that this has to hold. Still, if you look at it, that's one equation, two equations, three equations. And of course, we have four variables, V1 bar, V2 bar, and phi and theta. So we have two angles that have been introduced, but only one new equation. So, given theta, we could determine then all the rest of these if we knew what that one angle was. Of course, collisions among particles are incredibly important. That's how we make observations. The first observation of the nucleus of the atom was made using gold foil, by hitting it with alpha particles and looking at how those particles bounced off the nucleus. So collisions are very important for our understanding of physics, and of course we see everything that we see by using light. In other words, we shine photons on it, and photons have momentum also. So we can take a photon and hit an electron and look and see what happens, or some other particle. And one thing I'd like to mention here on these elastic collisions is if I have almost no loss of kinetic energy, an example of that is a bouncing ball that's sometimes called a super ball or a bouncy ball, and then I'm losing almost none of the kinetic energy. If I think about those balls bouncing, a super ball will bounce, come down and bounce and go back up to almost where it was before. And that's the incredible thing. You throw one of these things in a room, it just keeps bouncing and bouncing. In other words, this height is very nearly this height. Height before and height afterwards. Well, how much energy is lost? The answer is the energy here is mgh from wherever you drop this ball. So we can look at mgh before and subtract mgh afterwards. And look at this, and this will be equal to the energy lost. That'll tell us how much energy is lost. If you take things like a tennis ball, you'll notice often people drop them to see if they're dead or not. Have they gotten to the point where they're acting sluggishly? But this is to see how much energy is going to be lost in the bouncing of such an object. It may surprise you to learn that steel bouncing on steel is actually very elastic. It's one of the most elastic things. But I have to take a plate of steel that does not give any, So it has to be like a half a foot thick, 6 inches thick steel plate, and I take a steel ball and bounce it on it. It will lose very little energy. So this covers elastic collisions, and you'll notice again, I've left this calculation up to the reader, up to the student, to take this conservation of momentum, substitute in the conservation of energy for one dimension, and compute both of the two velocities, solving two equations and two unknowns.